My dear students, today we shall start another design of tension member. The problem is a diagonal member of a roof truss carries a maximum pull of 300 kN. Design the section and its connection with a 16 mm thick gusset plate. The length of the connection is limited to 340 mm. Design the lug angle also if required. The steel is of grade Fe410 and bolt of grade 4.6 are to be used. Now, for Fe410 grade of steel, Fy is equal to 250 MPa and Fu is equal to 410 MPa. The partial safety factor against ultimate stress is 1.25. Partial safety factor for material against yielding is 1.10, and partial safety factor for materials of bolts is 1.25. You can collect all those data from table 5 of IS 800. This is table 5 for partial safety factor gamma m, and you can see all those data. Now for bolt of grade 4.6, ultimate stress of the bolt is 4 into 100, that is 400 MPa, and factored design tensile force is 1.5 multiplied by 300 is equal to 450 kN. Now the next step is you can calculate the required cross-sectional area of the section which can carry 450 kN load, or you can go for calculating the number of bolt required to carry 450 kN load. So let me start from the calculation of required cross-sectional area. To calculate the cross-sectional area, you need two governing criteria. One is heat section rupture and that is yielding of cross section. You can calculate the net effective area by this formula provided in clause number 6.3.3 IS 800. This is 6.3.3 clause, and it is provided this formula to calculate the design strength of the single angle. But at right now you don't have all those parameters. That's why we can go for approximate equation. This is the equation TDN is equal to alpha ANFU by gamma m1, and you need to calculate AN. So AN is equals 1714.93 millimeter square. Now you need to calculate the cross section from this net section, and we don't know what is the actual cross sectional area. That's why we are adding approximately 25% of the net area. So the cross sectional area is 2143.6 millimeter square. And from the another criteria, that is cross section yielding, we are calculating the cross section directly, and this is 1980 millimeter square. The greater value will be under consideration. The greater value is 2143.6 millimeter square. That's why our first trial area is 2143.6 millimeter square. Now we have to follow the handbook. This is table 4 for rolled steel unequal angles. We are providing an unequal angle section, and you see this is the sectional area. In this column you can find the value of the cross sectional area, which is slightly larger than our required area. This is 21.56 centimeter square. This is slightly larger than our required area, and we can select this section, that is IS 150/7510. So let us try IS 150/7510. This is the section. Length of one leg is 75, length of another leg is 150, and thickness is 10 millimeter. The gross area of this section is 21.56 centimeter square, and the radius of gyration of this section is 1.59 centimeter square. We are collecting those data from handbook. Let us provide 20 millimeter diameter bolt, and the net tensile stress area of this bolt is equal to 0.78 into nominal plane shank area, that is diameter of the bolt. So this is equal to 245 millimeter square. The dia of hole is 20 plus 2, that is 22 millimeter. You can find this value from table 19. This is table 19, and you can see we are adding 2 with our diameter of bolt. So diameter of hole is 20 plus 2, that is 22. Now you have to calculate the strength of one bolt. Strength of one bolt will depends upon the strength of bolt in single shear and strength of bolt in bearing. Whichever will be the minimum value will be the strength of the bolt. So strength of bolt in single shear you can calculate by this formula, and this is 45.26 kilonewton. You can find this formula from IS 800. This is the formula to calculate the strength of bolt in shear. The clause number is 10.3.3. And to calculate the strength of the bolt in bearing, you need some parameter, that is end distance, edge distance and pitch distance. We are assuming some data here for end distance, edge distance and pitch distance, which is greater than the minimum value of end distance, pitch distance and end distance. So E is equal to 40 millimeter end distance, which is greater than the minimum end distance, that is 1.5 times of diameter of hole. And also we are assuming edge distance is equal to 40 millimeter, which is greater than the minimum edge distance, that is 1.5 times the diameter of hole. And we are assuming pitch distance 50 millimeter, which is greater than the minimum pitch distance, that is 2.5 times of diameter of bolt. Now we have to calculate KB. The KB value is the minimum value of those value, which is 0.5. So KB is 0.5. Now you can calculate bearing strength of the bolt from this formula, and this formula is provided by IS 800. You see this is clause number 10.3.4 for bearing capacity of the bolt, and this is the formula to calculate the bearing strength of the bolt. Now the actual strength of the bolt will be the minimum value, that is 45.26 kilonewton. Now the number of bolt required equals factorial load divided by the strength of the bolt, that is 9.94, and the number of bolt is 10. Let us provide 20 mm diameter 10 number of bolts with pitch distance 50 mm and edge distance 40 mm. This is the picture of this connection. Look at this picture. You can see 10 bolts are pressing in one line with pitch distance 50 mm. So total minimum length of the gusset plate is equal to 40 plus 40 plus 9 into 50, that is 530 millimeter. But in our question it is given that the limitation of the connection should be 340 millimeter. So this arrow indicates the length of this connection, that is 340. From this point to this point the length is 340. So our connection length should be under this limitation. Beyond this length we cannot provide any bolt or any gusset plate. So to reduce the length of the connection we need log angle, and please keep in mind we cannot reduce the number of bolt, because to resist the 450 kN load we need minimum 10 number of bolt. So we cannot reduce the number of bolt. What we can do, we can provide log angle and we can reduce the length of the connection. So let us provide 6 bolt for connecting main angle with the gusset plate and 4 bolt connecting log angle with the gusset plate. So total 6 plus 4, total 10 number of bolt is there. So this is the connection. We can do that. This is the log angle and this is our ISA 150/75/10. and we are placing 6 bolt in one line and we are placing 4 bolt in one line with the lug angle. So total number of bolt is 10. So now the length of the gusset plate or the length of the connection will be 50 into 5 plus 2 into 40 is equal to 330 millimeter, which is under limitation. Hence this connection is okay. Now you have to calculate the required sectional area of the lug angle. To do this, first of all, we have to calculate how much force it will carry. Now to calculate neat area, we are considering two paths. One is 1, 2, 3 and that is 1, 4, 2, 3. So you can calculate the neat sectional area. Along 1, 2, 3, this is 1930 millimeter square. B is the width and it is 215, and we have to consider this angle section as a plate like element, and the width of this section will be 150 plus 75 minus 10 by 2, and neat area along 1423 there is one diagonal line is there 4 2, that's why 1 p square by 4 gi will be here. So p is 25 from this point to this point, horizontal distance between two bolt, and the neat area along 1423 is 1726.44 millimeter square. The actual neat area will be the minimum of those two, that is 1726.44 millimeter square. This is the actual neat area, and this is also greater than our required or calculated neat area. That means this section can carry the tensile force, that is 450 kN. Now you can calculate the strength of the section, that is TDN is equal to 0.9 ANFU by gamma m1. You can see clause number 6.3.1. This is clause number 6.3.1, and the design strain due to rupture of critical section you can calculate from this formula 0.9 ANFU by gamma m1. So the design strength is also greater than the applied force. That means the connection is safe. Now you have to calculate the required cross-sectional area for lug angle. The total cross-sectional area of the section is 2150 millimeter square. We are calculating directly from this figure, that is 2150 millimeter square, and it will resist 450 kN factorized load. So 400 millimeter square will resist 146.5 kN factorized load, and the 700 millimeter square area is nothing but belongs to this 75 millimeter leg, and this leg will carry 146.5 kN factorized load. That means our lug angle which will be connected with this 75 millimeter leg, this will also carry 146.5 kN factorized load. Now the actual design load of the lug angle is 146.5 plus 20% extra with this, and if you can see the clause 10.12.2 of IS 800, this is clause 10.12.2, and it is saying that the developing strength shall not less than 20% excess of the force in the outstanding leg of the member. That means the lug angle should carry the load which is 20% extra of the applied load, and the applied load on the lug angle is 146.5 kN, and we are adding 20% extra with this, that is 175.8 kN. So the lug angle should be designed based on this load. So the required neat area we can calculate from this formula, that is 6.3.3 of IS 800, and the area is 669.96 millimeter square. So now we have to find the cross-sectional area which is equal to or greater than this value from handbook. But one thing you have to keep in mind, that the dimension of the log angle should be satisfied with the dimension of the main angle. That means our required area is 6.69 centimeter square. Okay. Now in this table you can see the greater value of 6.69 centimeter square is this one, 8.65 centimeter square. But the dimension of this section is 90/60 into 6. You cannot attach this type of section with ISA 150/75/10. That's why you have to choose the dimension of the log angle in such a fashion which can be attached easily with our main angle. So let us try this section ISA 150/75/8, which will be okay for our main angle, which is 150/75/10. Now we are going to check whether this angle will resist the applied force or not. We are considering two paths to calculate neat section of this section. One is 1 to 3, another is 1 to 4, 5. Along the line 1 to 3, the neat sectional area is 1560 millimeter square, and along the section 1 to 4, 5, the neat sectional area is 1396.88 millimeter square. So minimum value is the 1396.88 millimeter square, and this is the actual neat effective sectional area of this section, which is greater than our required value. That means this section can carry the applied force. Now the required number of bolt is nothing but applied force divided by the strength of 1 bolt. We have already calculated the strength of 1 bolt for bolt grade 4.6 is 45.26 kilonewton. So the number of bolt is 4, and now you have to calculate the number of bolt which will be required to attach the log angle with the main angle. In the clause 10.12.2 of IS 800, you can see the attachment of the log angle to the main angle shall be capable of developing a strength not less than 40% in excess of the force in the outstanding leg of the angle. That means the applied force on the outstanding leg of the main angle is 146.5 kilonewton, and we are adding 40% extra with this, that is 205.1 kilonewton. The lag angle should be carry this force when we are attached the lag angle with the main angle. So the required number of bolt is 205.1 by 45.26, that is 5. So we are providing 4 number of bolts for to connect the lag angle with the gusset plate, and 5 number of bolt to connect the lag angle with the main plate. And this is our connection. The red colored angle is the main angle, that is ISA 150/75/10, and the blue colored angle is the log angle, that is ISA 150/75/8. Thank you.